Well, this is EE 5721. This was the lecture that was to be given on 119. So we will now add version 2. Actually, there was another attempt at this earlier in the afternoon. This is still Monday, the 22nd. But I've been having terrible time with the video recapture program that the camera came with. But we're going to do it again here. So if we have a power plant, we put fuel into it, whether it's natural gas, coal, oil, or water. If it's water, then you draw a thing like this, and there's our impoundment, and we have a certain volume per hour, which is called Q, and we have a function out here. So we have Q of P, and here we have a certain H of P. But it's very similar, although for hydro plants we need a lot of other details going along with it. But with a plant like this, we send teams out to the plant. This is usually the kind of things that the mechanical engineers at a company will do. They gather data. I drew all these points. The idea of the points is simply that the data is not particularly uniform around this curve. We fit H of P to these points, and we say this is equal to A plus BP plus C P squared. Now that simply means that we're compromising. We're using a quadratic function, and we recognize fully that it's not a pure quadratic, but for the sake of this course. And we're going to say that there's a P min and a P max. For any kind of generator, the max is easy to understand, the rate at which you can deliver steam into a big steam turbine, the rate that you can deliver water to a hydro turbine, the rate that you can deliver gas into a large gas turbine, is all the mechanical end of the generator, and that there's a limit, usually depending on how the thing was designed. And the electrical part of the generator also has limits, as a max based on its current carrying capability and so forth. The min has a lot to do with the control systems that keep the fuel flowing into the plant, and those control systems don't operate, the turbines and so forth don't operate well below a certain minimum. So they like to get a power plant online, which means, again, that it is synchronized to the power system. The breakers are closed, it's synchronized, and they get it up to some plate within P min, P max. But they don't operate it down here, and they can't operate it above P max because the mechanical side simply can't push it any further. Now the fuel in the case of a steam plant is in MBTU per hour, and the P is in megawatts. Okay, so note that if we multiply both of them by H, then we get MBTU and we get megawatt hours. So megawatt hours is a unit of energy, and MBTU is a unit of energy. So it's energy per hour and megawatts, or it's just energy. Okay? Now, The issue that we have here in the course is this. We want to minimize the total cost of generation. I indicated in class on the 17th that electric utilities spend enormous amount, billions and billions of dollars for fuel. So being able to minimize the amount that they spend for fuel, even small fractions of a percent, end up being a lot of money and a big concern. So we'll start this out by saying we have 3 generators, and I'm going to label them 1, 2, and 3. So here's P1, P2, P3. And they are supplying a single load called P load. So the first thing I want to do this cost calculation is I want to take the H of P function, which is MBTU per hour, times the fuel cost. Now, it may seem strange, but I can do this as dollars per MBTU. That figure itself has to come from they would know what the dollars, let's say, per 1,000 cubic feet of gas, or dollars per ton of coal, or whatever. Now, if it's water, we're into a different regime. We're in a different way of accounting for things. Nobody sits there with a meter and says it's so many dollars per gallon for water. But we're going to just go around that, and we're going to say that we have a specific heat. We know how much MBTU per cubic measure of fuel we have. And so we're going to have a dollars per MBTU, and we're going to get a function F of P, which is dollars per hour versus P. Okay, so that's the right. I like to tell the story that operating a power plant is like having a conveyor belt with big bushel baskets full of $100 bills going into the plant to be consumed, and if you want more power, you run the conveyor belt faster. There's more dollars, so it gets more costly for more power. And so the mathematical statement of our problem says minimize the following: F1 of P1 plus F2 of P2 plus F3 of P3. And we're going to say subject to a constraint. In other words, this isn't an extra condition. That's P1 plus P2 plus P3 equals P load. Well, that seems reasonable. You want to minimize the sum of the operating costs with a condition that you're meeting that load. Now, there's other conditions that would say also subject to P sub I min less than or equal to P sub I less than or equal to P sub I max. I will often write this as P sub I with a negative there, Pi less than or equal to Pi plus. It's a lot quicker to write. And we could put I equals 1, 2, 3 for each of those. So this represents the economic dispatch problem. That's what has been the classical economic dispatch or economic operation problem for an electric company. And to solve this, Again, you will get a copy of these notes. You do not have to copy them off the video. You will all, along with downloading the video, you will have a PDF file of the notes themselves. So, to perform the minimization or the optimization, we use the Lagrange method. And the Lagrange method goes as follows. It says you build a Lagrange function where you put all the constraints into the function, and then you start basically taking derivatives and setting them to zero. That's how you find an optimum. Well, okay, first we're going to do it without, I'm going to say, do without P minus and P plus limits. Okay, so then our Lagrange function is the sum Pi, or Fi of Pi, plus lambda times P load minus the sum Pi. I equals 1 to 3. This should be I equals 1 to 3. Now, note in the text, this is designated as omega, and that must equal 0. And this is an equality condition or constraint. And then to solve it, you say the derivative of L with respect to P1 equals 0. So that means dF1 dP1 minus lambda equals 0. That's what you get when you take the first derivative with respect to P1. dL dP2 equals 0. So you get dF2 dP2 minus lambda equals 0, and dL dP3 equals 0. dF3 dP3 minus lambda equals 0. Last of all, dL d lambda gives you the same, and you set that to 0. That one simply gives you back P load minus the sum from 1 to 3 of Pi. So there it just gives it the constraint back. Now notice that for variables, I have P1, P2, P3, and lambda, and I have 4 equations, and I have 4 variables. You can put them in a matrix and just solve it, or you can very simply do it by just algebraic substitution. We'll talk about that in a minute. Note, the one thing you want to note right here, dF1 dP1 equals lambda is a result of the first equation. dF2 dP2 equals lambda. dF3 dP3 equals lambda. And that says that all generators operate at the same marginal cost. Now, a little caution here. The economists insist that if you have a cost function f, then the first derivative of the cost function is the marginal cost. That's the change in operating cost for a very, very, very small change in P, which is the first derivative. The power industry back sometime in the early 20th century called this incremental. And Now, nomenclature being what it is, that essentially says the same thing, but the economists don't like that. They like to use marginal cost and incremental cost for a change of no matter what the size delta P is. Well, I'm not going to go into worrying too much about that. The term marginal cost is the preferred one for economics people. All right, and so if we have f of I pi is ai plus bi pi plus ci pi squared, then df dp equals b plus 2c. I'll put the I in here. Pi. So it's now a linear function. And it looks like this. And we'll assume that this is the minimum and this is the maximum. We're not going to worry about where it's going to go outside those points. So it rides up this linear cost function. Now, if I drew the incremental cost functions for our three generators on 3 pieces of graph paper, and I lined them up on a table. Let's say I taped them down, and I made sure that the 0 point were all lined up horizontally, and that the df/dp scale was the same. The df/dp scale on the vertical axis was the same. And this is P1, P2, P3. So this is df1, dp1, df2, dp2, df3, dp3. And let's say this one looked like this, and this one looked very, very low slope, and this one was a very steep slope here. That's okay. Now, if I wanted to get a dispatch where the same incremental cost applied to each one, I could draw a horizontal line, and then I could say, well, it intersects there, so that's P1, and that's P2, and that's P3. Now, the problem is that particular line might not be apologize, I had to jump up and go to another desk to get the red pencil here, the red pen. But that might not be the total. In other words, we take this, let's say this is pi, and it's the first solution, so I'm going to put a superscript 1, P11, P21, and P31, and I'm going to add them up. P11 plus P21 plus P31, and I'm going to compare that. I'm going to say equal to with a question mark P load. Well, suppose it isn't. And suppose it's too small. Well, what should I do? What I should do is I should take my ruler that I have here and just draw another line, the red line, across like this. And now I get a different set of intersections. Notice that this one really zooms up. This one hardly moves. So now I get P12, I get P22 and P32. So now I can say P12 plus P22 plus P32, and I can compare that question mark P load. So all I need to do to calculate the exact economic dispatch with these linear functions is to move this line up and down until the sum that I calculate. Every time I move it, then I calculate the intersection and add them up. and test that. Is it within the P load value that I want? And you can say, well, okay, if it's within 0.01 or 0.001, you're good enough, and then you can stop. And then you will have equal incremental cost on those three generators. Later on, we will show you that can be formalized into what is called a binary search, and it's very powerful because it takes care of all the limits in a very simple, elegant manner. Okay, now let's come back to our mathematical. Remember we had 4 equations and 4 unknowns. So basically B1 plus 2C1 P1 equals lambda. B2 plus 2C2 P2 equals lambda. And B3 plus 2C3 P3 equals lambda. P1 plus P2 plus P3 should equal P load. And the simple way to do this, other than building a 4x4 matrix and inverting it, is simply do this. Say, well, okay, P1 from the first equation is lambda minus B1 over 2C1. Similarly, for P2 is lambda minus B2 over 2C2. P3 is lambda minus B3 over 2C3. I just solved each of these. And then down here at the bottom, I take each of these values and I plug it in here, and I'm left with an equation that only has, the only variable is lambda. And now I can just solve that. I have to work out the denominator, numerator, blah blah blah, and I get a solution for lambda, and then I can plug it back in. I get the economic dispatch. So that's what economic dispatch is all about. But it does get to be more complicated than that, as we will find out. Well, the next thing we're going to do here is we're going to take and draw our function again, f of p. We originally said that it's like this. F of p is a plus bp plus cp squared. Here's p going down here. Now, suppose for some reason I wanted the curve to be a quadratic function going this way and then a different quadratic function like this. F of p. What would the df dp? Remember the df dp for this one is simply a straight line. Simply a straight line. Here, the df dp is a straight line, and then all of a sudden the slope you notice at the very end here does a jump when it gets onto the next segment. So the slope looks like this. This is what's called a piecewise linear incremental cost curve, okay? Piecewise linear. Here we go, incremental or marginal cost function. Now, this might look a little exotic, but the way the power system operates, these slopes determine how the various units load up one versus the other. And yes, this data should all be related to the tests that the mechanical people did, but the people that operate the system know that they don't want certain slopes to cause one generator to race ahead while the other generators sit, and so they adjust these to get certain operating characteristics. So we'll come back and talk about piecewise linear curves, but they are very practical, and that lambda search technique works beautifully on piecewise linear because you come in with a value of lambda up here, and it's just a matter of proportioning. If I came in with a value of lambda like this, well, and I know the point down here, then the intersection I can calculate because I have the slope. I can calculate the new p over here very quickly. So it's just a couple of multiplies and add, subtract, and it's done. No quadratic or anything to solve. All right, now the next thing we're going to talk about is the homework problem that you've been assigned. And page 5, no 4, right? Let's get it right. This is 4. Pardon me. Page 4. Google Drive has a directory called, it's Google Drive ECE 5721, and it's called Homework, not surprising. And it's in its own directory. And I will always number them like this: Homework 1, and then I'll put due January 27th. Homework 2, due January, whatever it is, so that you can always tell which assignment it was and when it was due. So homework 1 is going to have a problem. The first thing it's going to ask you to do is problem 3.2 from the text, which involves a lot of graphs. And the graphs, my recommendation is to use either MATLAB or, even easier, use Excel. You can put the data in and get the graphs out very quickly that way. And we want you to plot those graphs and look at them. And then we're going to do what I'm not aware of. You can hear me still fighting against this cold that I've had. Okay, we are also gonna do problem 3.3 on in the homework. So those two problems, but then we're gonna do a takeoff. We're gonna say using the two generators in problem. What did I say here? I'm sorry. Problem 3.1 in problem 3. It's either 3.2 or 3.3. But I want you to concentrate right now on this problem 3.1. The two generators in 3.1. And they're going to load to 50 megawatts of load supplied by those two generators. And this is the way I want you to solve it. First, ignore min max, which for those generators are 20 megawatts min and 100 megawatts max. So with two of them, it can go from 40 to 200. They're both operating 40 to 200. So there's the limits, but we're going to ignore them at first, and you're just going to set that up, with Lagrangian equals f1 of p1 plus f2 of p2 equals lambda times 50 minus p1 minus p2. Be sure that you make sure you're not using h of p, you're using f of p. You've multiplied h by the fuel cost that's given to you in the problem. Okay, you're going to solve that. And then you want to ask, does the solution meet all p min and p max constraints? And in fact, it doesn't. One of them will come out below its low limit. One of them will come out below the low limit. So we're asking, and to put it differently, if P1 minus less than P1 less than P1 plus and P2 minus less than P2 less than P2 plus are that this, if this is met, then they're both within limit. Or if P1 is less than P1 min, or P1 is greater than P1 plus. And similarly, or P2 less than P2 min, or P2 greater than P2 max. So it's either within limit or less than the low limit or greater than the upper limit. And these conditions we don't want. These are okay over here. Same thing down here. And to do this, we use something called the Kuhn-Tucker conditions, or KKT. I like to tell my students that when I was a student, it was called Kuhn-Tucker, K-U-H-N, Kuhn-Tucker conditions. They're two professors at Princeton. And then people discovered a paper way back. I don't know which came first, but this other paper by Karush had dealt with the same problem, come up with the same solutions again, and the compromise, instead of changing the name completely, was just add Karush on there. So it's KKT conditions. Now, what it's good for, these conditions, is allows you to test to see if a solution is optimal and obeys all constraints. But it does not give you specific instructions as to how to get to that solution. Now you might think, well, this is kind of silly with only 3 variables. Believe me, if you have 10, let's suppose you have 20 or 30 generators, each of which could have an upper or lower limit. It's not at all obvious which ones are on their limits, on a lower limit or an upper limit or not on any limit. It's not obvious. And how do you get to the solution requires smart algorithms, and that's what we're going to talk about in the next couple of lectures of the course. So now we have this Lagrange function, Fi Pi plus lambda P load minus the sum Pi, I equals 1 to 3. So there's our initial problem. And now we have these inequality conditions. Oh, I'm sorry, we're doing the homework problem, so this is 2 up here. We're still doing the homework 1. Pardon me. So we've got 2 generators, and so we've got to worry about P1 minus less than or equal to P1 less than or equal to P1 plus, P2 minus less than or equal to P2 less than or equal to P2 plus. And the way you do this is you add to this the following. You say the sum of Fi Pi plus lambda times P load minus the sum Pi plus, and now I have to add 4 more constraints, each of which has its own Lagrange multiplier, which we use the variable mu. Mu1 times P1 minus P1 plus mu2 P1 minus P1. Plus, and we have a sort of a mirror set for P2 minus P2 plus mu4 P2 minus P2. Now, each of these, this is of course an equality constraint. Each of these is an inequality constraint. And we're not simply going to be able to just find mu values that will take care of this without treating it in a particular way. And the way to handle this is to say that for inequality constraints, in our case, let's take mu1 times P1 minus P1 plus. Either mu1 is equal to 0, in which case, if we're trying to drive this to 0, then P1 minus P1 plus, I don't care what that number is, because this doesn't come into the calculation. Or mu1 is greater than 0 and P1 minus P1 plus equals 0. This is what we say the constraint is active. A constraint is active when it's up against the constraint and it's being held there. We say the generator is up against its upper limit and we're holding it there. In which case the mu is giving us some numbers. Later on we'll come back and we'll indicate that gives you a value. It gives you some useful economic information about what this limit is costing you. If mu equals 0, then this thing doesn't matter. Okay? Now, so to solve df1, dp1, I'm sorry. Let me back up. dl, dp1. Remember L. If I go back up here, dl now has, here's L. It has the cost functions, it has the equality, and it has these 4 equation terms for the inequality terms. So this now gives you df1 dp1 minus lambda plus mu1 minus mu2 equals 0. dl dp2 is df dp2 minus lambda plus mu3 minus mu4 equals 0. And then dl d lambda just gives us P1 plus P2 equals P load, which happens to be 50 megawatts. The problem now is that we still don't know what, we have 4 different variables, and mu can be 0, or mu can be greater than 0. So we have 4 variables. That's 16 possibilities. 16 possibilities. And if you look at it long enough, you'll say, Professor, that's not quite the case, because if one of them is against its upper limit, it can't be also against its lower limit, so etc. So you can cut that 16 down, but it still doesn't tell you which ones are at the upper or at the lower. Okay, so what I want you to do in the homework is as follows. You're going to take and you're going to solve, let's say that the one generator came out at its upper limit. It's actually a lower limit, but I want to use the upper limit for this example. So if it solves, solution has P1 greater than P1 plus, then I'm going to force P1 equal to P1 plus. Okay, so that P1 minus P1 plus is equal to 0. They're equal. It's an active constraint, in which case mu1 equals 0. Okay? I'm sorry. Mu1 is greater than 0. And mu2 equals 0. And I'm going to force the constraint, and then I'm going to go back and solve it. And I'm going to solve it as follows. Let's come back and review this again. Solve the two generators in 3.1 with no limits. Okay. And in this case, P1 solution, we're going to say suppose it came out greater than P1 max. You'll have to solve it and determine if that's the case. But if it came out greater than P1 max, then we have to force it P1 solution equals P1 max. If we did it so that P1 solution was less than P1 min, then we would say, no, P1 solution is going to equal P1 min. We're going to force it. Now, in this case, you're fortunate because you get a solution where only one generator hits a limit. You might want to think about it for a minute. Could I have two generators, and without looking at limits, could I have one generator that's on its min and the other one that's on its max? Now, how do you get a solution? And all I can say is that if you do that, then if you're down to that, things are so tight then. As soon as you put the minimum one up to its minimum, if it was below minimum, the other one would have to come down. And if it came down below the max, that's the solution. Okay, but anyway, let's take this case here. Let me now write the Lagrange. Let's write it for this. This is the case that you have in that homework problem. So L will equal the sum Fi of Pi plus lambda P load minus P1 minus P2 plus mu2 P1 minus P1. And that's the. Now we don't know what this is for that generator, but we know that if we ignore this thing, P1 will come out less than the limit, and we don't want that. So if that's the case, we're going to force it to its min, and we're gonna make this equal to 0. Then mu2 we'll jump down here. Then mu2 will come out to be greater than 0. Okay. If it's at its limit. So this looks like this. We say d L dp1 is equal to df1 dp1 minus lambda plus mu2. We had mu2 up here. And that's got to equal 0. dl dp2 is simply the old, because we didn't include its limit in the problem, minus lambda equals 0. P1 plus P2 equals 0. That's the derivative of L with respect to lambda. So there's the three constraints. But wait a minute now. I've got a fourth variable in here, and that's just going to have to be dealt with. But and dealt with meaning it's a number greater than 0. It's a number greater than 0. But if you force P1 equal to P1 min, or P1 negative there, then you automatically know the value of P2 is equal to P load minus P1 min. And so now I have the P solutions, and now I can back out the values of lambda. I can get that from this equation, then I can get the value of mu. And the way it will look is like this. Here's the segment for that generator, and here's the upper and lower limits, and the lambda will be up here. This is the number here, which is df1 dp1 at p1 equals p1 max. If we're dealing with, I'm sorry. I drew that wrong. I just told you that we were going to deal with it as a min. Here's lambda. Here's df1 dp1 at p1 equal p1 min. Well, the difference between these two here and here is mu2. Okay? That's mu2. Because the equation says that df1 dp1, that's this value minus lambda. Well, there's some difference there. Then it says plus mu1 equals 0. So when you take this and you subtract that, then there's a little bit left over to get to 0. Okay? As promised, this will be in Google Drive, and you'll see a WMV file. I recommend VLC. That's a very, very good free software as a video playback software. You will also get a PDF of the notes. I will post these this evening. It's now about 7:30 in the evening. Trusting that all my efforts have resulted in a successful video. We had a problem, and all I can say is I'm not sure why it was shutting off. I hope I have simply made enough changes to the video recording to get it to work. Okay? I will be posting that shortly. So we'll see you tomorrow afternoon at the 4 o'clock session.